I see several people here.
So I think I can introduce you first, and then we 2 more minutes.
Yeah, no problem.
Okay, thank you guys for coming here. Today is our honor to invite the Professor Shinan Liu come here to give a talk. So Professor Shinan Liu is the assistant professor at the University of Hong Kong, where he directs the networked AI systems in Security Lab, NASA Lab, in the Department of Data and Systems Engineering. He earned his PhD and master in computer science from the University of Chicago, advised by Professor Nick. He is the recipient of the 2025 Machine Learning and Systems Rising Stars in something like that. And he previously served as the head of the NSF Action AI Institute Student Advisory Council. His research lies in the area of computer networking and security, with a focus on developing accessible, reliable, and perform machine learning systems for network data analysis in employing network data analysis for critical issues in security and privacy. His work has appeared in top-tier conferences and journals. They also serve as the program committee members and previous task force members for some very famous verses. In his research has also been covered by media outlets, including the Wall Street Journal and ACM Tech News. And so, like, yeah, let's welcome the Professor Liu to begin his.
Cool. Yeah, thank you, Minhan. And hi, everybody. My name is Shinan. I am currently an assistant professor from University of Hong Kong. Thanks to Minhan and Professor Wang for the invitation. It's my great honor to give a talk here. So today I'll be talking about the promise of generative synthetic data in network intelligence systems. So my domain is in computer networking and security. And I believe the problems and principles I talk about today can be also extended to like domains beyond just networking. So this talk summarizes our recent endeavors on improving like network operation, for example, some like network management and security tasks. And feel free to ask me questions during the talk. And basically, I analyze a lot of things from the angle of synthetic data. Okay, so let's get started. I want to start my talk with a pretty big question. What do you think would be the next modality for AI foundations? So the biggest technical advancement we are seeing in the past 3 years is the adoption of large models. It has revolutionized language and vision. They are enabled by the entire internet of open text or images, so that they actually have a very strong zero-shot generalization capacity. But what could be the next modality for these AI foundations? So I thought about this question a lot, and I found that the only data to compare in its volume would be those operations data. So these real-world industrial data, such as some system logs, some network traces, time series, tabular data, could have massive potential for the next wave of opportunities. You can find this type of operational data in many scenarios, such as in networks, manufacturing, automobiles, robotics, healthcare, and a lot of other domains. But unlike text or images, there are major bottlenecks working on AI for these operational data. So the first bottleneck, as I see, is the data availability crisis. The key limitation today to train large model is no longer compute, because we have really efficient ways to do that, but access to these vertical specific high quality data in our real world operation. The second bottleneck is the system performance, because ML is actually a pretty heavy process, and this operational data has such a big volume. So basically, working on them will impose a very high data utilization cost. So today I will be talking about this AI for operation inside networks as a major example because that's my field. And let's recap some networking 101 to begin with. So inside a network, a computer network, there are a lot of computer nodes, and there are often like clients and servers. So basically, when they are communicating with each other, a network flow will be established, and within this network flow are a sequence of network packets. So if we observe these network flows and their dynamics, we can enable two types of tasks in this domain. So the first type of task is in network management. We can take a look at their latency, their throughput, and try to understand the resource allocation and have like a better strategy for that, trying to forecast their demand. That is network management. The second type is mostly in security analytics. So by looking at the patterns within these network flows, we can try to understand whether there are intrusions, malwares within these networks. So recently, we're seeing a trend of people applying machine learning on a lot of these analysis. The main reason behind it is like now 96% of the web traffic is encrypted. So that makes a lot of the previous methods working on the unencrypted payloads obsolete. So now people have to look at the patterns between the packets, like their interarrival times, like their throughput changes, and try to get a pattern from this. However, if we really deploy these models inside the real world, we're often seeing a huge gap between what is promised in our, for example, some academic projects versus the actual real world performance. And why is that? So basically, that like draws back to the previous two challenges I have just talked about. We as a community, we do not have an equivalent of an ImageNet as in computer vision community. We have some open source data sets, but they are often pretty old and limited in their volume. Tech companies have a lot of data, but they won't share it because of customer privacy, and they don't want people to analyze their internal systems. So as a result, for people in academia, it's really hard for us to access this real world high quality data for many network analytics vendors because they cannot see like the data from other organizations or entities. So they cannot really build models that's reliable enough to generalize to different like situations. The second challenge is this high data utilization cost because nowadays the networks are just like too big. So if we put them into numbers, basically we have 175 zettabytes of network data in 2025 that was generated. So it's a unit that maybe many of us are not familiar with. So any like operation storage of this data is like a big problem. So how can we deal with these two challenges? In this talk, what we want to argue is that synthetic data could be a very promising solution to deal with these two challenges. So to start with, what is synthetic data? These are the data that are artificially generated, and they can reflect at least partially like the characteristics of some real world data. Suppose we have a data owner and they have some original data or some understanding of the original data within like certain data boundaries. And then we can use a targeted or just like a full generator to create the synthetic copy of it. It reflects the characteristics of this real world data, but they are not real. So by generating them, we can essentially enable like data sharing after this process. So later, like the model developers, network operators can all work on this data. So in this talk, I'm going to like center around synthetic data and try to answer two types of questions. The first is that how to create the synthetic data with high utility, high enough that it can actually be useful for many downstream real world operations. And the second is that how can we use this synthetic data to cut the end-to-end system cost in our real like downstream ML applications? So I'll be basically covering a bunch of work from our lab. And well, yeah, let's start from the first bottleneck, basically the data bottleneck. But before we dive into the system designs and everything, let's try to understand like the real pain points when we are trying to use like this operational data. The first pain point is that we do not have enough realistic data outside many of these data boundaries. So, for example, there are many network management or security companies. They possess a large amount of network traces. However, due to many reasons, such as data governance rules, internal policies, privacy constraints, it's very hard for another company, another country to get access to this data. The next pain point is that we do not really have enough interesting data. So even if we have a full infrastructure to collect a lot of data, what people really care about are those rare cases. For example, for network operators, that's tail events, which are in the 95th or 99 percentile. For network security engineers, those are like security incidents. And those are events which are scarce by their nature. So if we use it to train like machine learning models, this will cause data imbalance issue. And if you do not have enough data on certain classes, you will not perform really well on those classes. So basically, we want to get more of this interesting data. So how can we deal with these two pain points? The answer is still in synthetic data, as I argued earlier. And in the network domain, basically the synthetic data we can see is generated a lot by these traffic generators. So let's take a look at this progression timeline for the whole traffic generator involvement. Basically, there's one takeaway I want to share with you is like all these existing generators, they either cannot really capture this real world complexity or they are just too cost-grained. So before 2015, there are a lot of heuristics-based methods. Those are like the rule-based simulators, emulators, and basically we can control them very easily. We can define the number of network nodes, define their topology, define what protocol are being running on them. So we can actually get very fine-grained information coming from it, such as like the information in like every single bit of each packet. Yeah. Uh, However, the downside of this approach is that we cannot really simulate the real world complexity because there are just like too many applications in the world. For example, we might have like tens of thousands of or even millions of applications on the internet, and it will take like an expert like several days to reverse engineer, for example, YouTube, like what does the flow look like and how does it really operate inside real life. So it's very hard to scale. And these simulators, they like a single machine cannot simulate more than like hundreds of machines. So it's really hard to compare with this real world complexity. So later in our community, we start to think about, okay, if these simulators won't really work, can we do it from a data-driven perspective? And it was back in 2022, even before ChatGPT was out, there are a lot of methods using GAN to generate this network traffic. So they actually can learn this complexity through this data-driven approach now. And some work I want to highlight includes this doppelganger from IMC and NetShare from CCOM. CCOM is basically the best conference in networking. So basically, these models are really good at capturing like long-term dependencies. However, because of the limited capacity of GAN, they are not really able to generate a lot of like fine-grained output. For example, the maximum they can generate per record is like 20 features. And it's really hard to teach a GAN model about network protocols. Basically, the network protocol is very strict, but these like GAN-based models are pretty like probabilistic. So it's really hard to do that. And then it was in 2024, we saw like an emergence of more capable models, such as diffusion models. And we asked ourselves, can we actually get the best of both worlds? Like
Yeah, sure.
not only get the real world complexity, but also get fine-grained output from the network traffic. So one question we start to ask ourselves is like, okay, the world is really complex. How do we really capture and describe such complexity? And we found that, oh, actually text is a great medium to carry many like abstract meanings. For example, this concept of application or the concepts of, for example, some specific protocols or layers. It's very hard to define it like super specifically, but they are basically like a combination of characteristics for this network operation data. So what we're advocating here is a text to traffic synthesis paradigm. We will describe the network traffic and show one example to our model, net diffusion. And then you will give us some very diverse raw network traces. It's actually the binary files of the packets that we generated. So this is a hard problem, right? Because in order to generate the binary files, they have to like fulfill all these protocols. And there are many inter or intra-packet dependencies within them. And one anecdote I want to share with you guys is that when we released Net Diffusion, one of my friends in Google Cloud was really excited about it because oftentimes they need to configure, for example, their firewall systems, but they don't necessarily have the traffic to test against these firewalls. But now we can just tell like Net Diffusion, okay, help me to generate a Netflix traffic coming from US to China, which is encrypted by VPN. Then this model will be able to give you that. So one of the most interesting and also challenging problem for this operational data is that they have many dependencies across rows, across different columns. They also have some temporal correlations. And for this network data, that is about the stateful network protocols. So if we are generating an image, say we want to generate a dog, it does not matter where the dog is in this whole image frame. However, they have to follow this statefulness in network protocols. And how to deal with it? We came up with two insights after we observed the characteristics of network flows. First insight is that we found that actually network flows and images, they are mutually convertible. So, and each of the network flows is composed by multiple packets, at least a few. So we start by answering the question like how to represent one raw packet. And now also like networking 101, basically computer networks are having like multiple layers. And the data itself will be encapsulated by headers after each layer. For example, IP layer, like transport layer. So basically, we're adding some headers when these packets traversing across these network layers. So based on that information, we used one pretty standard encoding method, which is called mprint. So mprint is a bit-by-bit representation of network traffic. Basically, for each of the like common network protocols such as IPv4, TCP, UDP, we just like translate all these 0 1s as it is in this 0 1 representation. And if, for example, like this TCP, then the packet has TCP, then it does not have UDP. So then all the UDP fields will be padded to be negative ones, and vice versa. And also, for example, for IP, headers, there are not all the headers have all the fields. So some of them are also padded to negative ones. And by doing this, we'll be having like a constant size of vector for each of the packet. And in all of my work, we don't care about the payload because now every payload is basically encrypted. It does not make any sense to learn from encrypted information. So next, we convert these flows into images. And one challenge we face is that one flow have several to thousands of packets. So basically, we adapt this endpoint encoding to images. For example, here we have an example task, which is trying to do service recognition, looking at one network flow and say whether this is from YouTube, from Netflix, from some other applications. Yeah. And what we do is like we stack the endpoint representation together and do this like pickup to image conversion and generate a prompt associated with it. So on the right side is our actual representation of network flow. So each of the row is one packet, and each of the column is one bit in the header. As you can see here, like the original 1 and 0, they are encoded in green and red. And all the negative ones here, they are basically the gray area. So the beauty of this representation is that it actually can be converted back into these packet captures. So we can like actually use it once it's generated, like for example, another image is generated, and then we can convert it back into usable packet captures. Our next insight is that we can actually map a lot of protocol constraints into the spatial structures of images. So for example, if we extract the edges of this representation, it actually have a lot of protocol structure information. For example, from these, we can understand what are the protocol choices, the configurations of these protocols, some frequent bits across different packets, and even some, for example, state transformation information. Yeah. So based on these two insights, we design net diffusion. Net diffusion aligns its generation with these network protocols. And the basic idea is that we want to adapt this nicely trained generative text to image model on the image representations of network traces. So the first step would be converting PCAP into images as we described. Then we will fine tune a like text to image model. And many of you may have tried it. It's a stable diffusion model. And then we will do some controlled generation and correct any mistakes during this generation process. So since we already talked about the first step, let's talk about some of this fine-tuning, the second step. So the goal for this step is to let the model recognize this unnatural image. Yeah, sure. Yeah.
The image in the last slides, like the bat level.
Yeah, like something like this.
Okay.
Yeah. So there's a question from the audience, and let me repeat it to the online audience. So basically, yeah, Minghan is asking the output of this data. So from the model itself directly, that would be the image, which looks like our representation earlier. But in the end, we will be converting it into the binary files. And that is basically the PCAP a lot of like networking researchers are using. Yeah. Great.
So in your representation, is it possible that you have a super long image because you can have
Yeah. That's a great question. So basically now we are representing it in like a 1024 by 1024. So that's the limitation of this representation. And that's also one motivation for our next work, which I will be talking about it later. Yeah, thanks. So basically like we have a length limitation here for the representation. Yeah, it cannot exceed 1024 in this design. But say if this like backbone model is improving, they can, for example, do 2048 by 2048, and then we can get like a more verbose version, like a longer of it. Yeah.
I'm just curious about the training data
Uh-huh.
set, because you have to curve the data, right? So
Yeah.
it's kind of for the stable diffusion, if you wanted to train a model, you have a lot of the data.
Yeah.
For the networking, how about the size training time?
Yeah, so Minhan is also asking about the training data size. So here, because we have a pre-trained like image model, that pre-trained image model can help us to do a lot of like, for example, working on the edges and use the image based approaches to deal with it. So in our fine-tuning stage, we use, for example, 100 samples for each classes, and then we can already do fine-tuning pretty well. Yeah. Good. So let me proceed. Basically here we fine-tune this off-the-shelf model and let it to recognize these non-natural images. And here we have a default output for the input Amazon traffic. You can see the fine-tuned output learns the color schemes and learns the stripes, but it's not perfect. It's not what we really want. So it's not enough. So the
How about the color? Like, I remember you said you had three colors to be surveyed, right?
yeah. The three colors are red, green, and gray, which is basically learned in the fine-tuned output. But like if we don't fine-tune it, it's just like default output. It's like
Not fine.
yes. It's just like the original diffusion model.
Oh,
Yeah. Right. Then the most interesting step and most important step in the whole pipeline is this controlled generation. So we'll still need to align or the protocol utilization across and within packets. So when we enforce this control with the help of control net, I believe many of you working in computer vision is familiar with this. So basically, by utilizing control net, it enforces the generation along with these edges. And also we with the help of like the input like example here, the one prompt. And then you can see that our generated data is much more constrained. They have this form already, and but still it's a little bit fuzzy. So at this stage, it does not really can be converted into like a full-fledged packet capture file. So our last step is like a post-generation verification, because there are many like dependencies within and across packets. And some of the dependencies are mathematical operations, such as like computing the checksum of certain fields. So these, I think, no matter what, like generative models cannot really generate those. So basically, we enforce these rules by correcting like 5% of the bits, and then we'll be able to have the image that can be converted into PCAP, and this PCAP will be compatible with many network analysis tools with no errors. So how good is this generation? Here we have one meta evaluation. Basically, it's looking at the statistical differences between the original data and the actual generated data. So that is quantified through the metric JSD. So the lower the value, the better. And here we have two data formats. Basically, that's because we have two models. One only works on NetFlow, one works on the PCAP. And we can see that for our model net diffusion, it gets a smallest distance, which means that it's like doing the best in this reconstruction. And how are we going to use this data that's been generated? So we have two major use cases. One is that we can actually use these compatible traces with many network analytics tools to do some analysis. And we can leverage this data we generated to increase the testing coverage of many network infrastructure. As for example, if we put our generated data into one of this like tool, you can see all the attributes can be recognized, and it also has a strict time order. Nothing is really strange. So it basically is like it shows this protocol level compliance. And our next use case is about improving machine learning models. You may still remember our second pain point, which is that we do not have enough interesting data. So how about we let these generative models to generate those rare cases which we are really interested in. So here we are comparing two generative methods that share the prior art and then net diffusion. Then we train like three different models to work on this 10 class classification task. So what we really care about is this delta accuracy because it shows like how much benefits the synthetic data can bring in. So here, like for next year, after we incorporate the generated data, the accuracy slightly dropped. Yeah. But for net diffusion, one thing to notice is that we start with like a much higher accuracy because net diffusion works on very fine-grained representations. And what's really interesting is like the delta accuracy slightly improves. And if we zoom in into these rare cases, like rare classes, which was previously very imbalanced, well, now we're able to add a lot more diversity into them. And on this like holdout data sets, we're able to improve the accuracy by a lot. So
this results is for 10 class service recognition task.
yeah, yes.
If we scale up to the 100 classes, or how about the results?
We haven't tried that yet, but like basically we tried like a 50-ish classes. It's improving. Yeah, definitely, especially for those undersampled ones. Later I will show you like a use case where we're trying to really help network security task. And by adding those more diversified samples, all those classes will be basically coming from like 10% accuracy to like a 70% accuracy. Yeah. So net diffusion has attracted a lot of interest from the networking community. It has been integrated into Net Microscope, this startup company, and we have also attracted some initial collaborations with Alibaba, Netflix, and etc. So here you can see like it's open source on GitHub. If you are interested in that, feel free to scan it, or you can just type and search net diffusion. Yeah. Great. So net diffusion was a work that we did in 2024. And we did a lot of like a retrospective thinking on that. And we many thought about like what's still missing in this type of work, right? So we found that some of the biggest issue for net diffusion was first, there are still some external prior needed. So what's clever about a net diffusion is that we really have this controlling component, but the control information is some structures we impose like as a prior. If, for example, we really want the model to learn these structures by itself, this becomes a burden. And then we also need like the post hoc, like this verification thing to help us, which is less ideal. And also, thanks for your question earlier. Basically, we also noticed that the context is actually not that much. For example, in net diffusion, you only generate 1K packets per image, which is not able to really capture some really long range dependencies. Like as in, for example, video conferencing, some video streaming applications that's like well above like the 1K packet window. Yeah. The third thing is that there are a lot of like it's basically being modeled as isolated flows. Yeah, it's basically we take a look at Netflix and strip it to each single flow, but real sessions they interleave a lot of different components like DNS, control some data across these flows. So there are also some these like multi-flow states being involved in here. So how to deal with these issues? We noticed that there's an emergence of like a very good type of model, state-space models. I believe a lot of you working on generative AI also are pretty familiar with it. And it somewhat naturally deals with these shortcomings. For example, the first is that we need some external priors in net diffusion, basically to provide control and also the post hoc correction. That's because this network traffic is inherently stateful, and they are pretty sequential across packets. So one model like state space models, they are designed to learn these hidden states on its own. And then basically we don't have to impose these structures as a prior in it, which is really good. And then also because like the state space models or Mambas, they are very efficient during generation. So that gives us like a more capacity, more context window within the similar amount of compute. By doing that, we are able to really have a longer term dependencies captured in these models. So here we take a look at some real examples and found that okay, when we look at this multi-flow traffic, they can actually be modeled differently. They can be modeled more like interleaved conversations. So basically, these applications they are a symphony of multiple flows. And what we do here using state-space model is that we just mix it and give the tokens to represent different application, different flows, and then that itself could actually be learned pretty well using state-space architecture. And the second is this longer term memory. This enables us to capture longer dependency across protocols. Because, for example, in regular sessions of TCP, you have to have a handshake first. Then it's a long data transferring. Sometimes there are like some anomalies or some retransmission, and that's also it. And then there's teardown. So teardown only happens after you transfer the data. So, and that is like a pretty long, to be honest. So basically, using state space models, we are able to remember the packets that's beyond, for example, 10,000, this window. Okay, so we did like some fundamental changes to our generation framework, and now we basically frame this as more like a sequence modeling problem. We use Mamba 2, and we have some like a pre-processing tokenization, basically trying to have this pickup as tokens first, and then we do some pre-training instead of doing fine-tuning, and then we have this generation process. So you may wonder how good is this modeling compared to the previous ones. Here we evaluated like across several different metrics. The first is this downstream utility. It's still like this 10-class service recognition task. And we're basically trying to mix the real versus synthetic data and test it on some held out real data set. So the x-axis you can see here is a mixing rate, with 1 being 100% of the data is synthetic data. And the y-axis is accuracy. So on the right side, so left side is up level, right side is the service level. So the up level is like more fine-grained. Yeah. So what we can see here is like a net SSM, the data generated by it is very stable. Like even when sometimes the mixing rate, basically we just train entirely on synthetic data. And then you can be as good as you train entirely on real data. And when you test it on like this held out real data. So that basically shows it's pretty consistent. But there is one possibility here is that maybe NetSSM is just memorizing all the data. So when you generate it, like you train on it, and then it's just like as good as real data. So we tested on this aspect and to see whether these generated data are memorized or actually diversified from this output. Here we have several metrics. First is like a byte for byte identicalness. Yeah, that's actually really very low, 2%-ish. And then we also take a look at like a 5% Hamming distance of any training packet. And that's also low, no more than 4%. And we also have a pretty decent diversity ratio. So this shows that this model is really diversifying the traffic, not memorizing it like on a very large extent. So one final thing I think I want to show for NetSSM is that it's actually very good at keeping the semantics, which is especially captured across multiple flows. So the question comes down to like, does this synthetic traces, they really behave like real applications? So here we use one case study. For example, when we do video streaming on Netflix, um, in real world, you have like many parallel flows being generated, and there are some prefetching effects. But basically, sometimes it preload some video chunks, and so basically you have like the periodical refills or like the throughput will change periodically. So here I want to show that on the left side is what we generated. Basically, we put like this 2000 packets as a prompt and then let it generate later. And compared to the ground truth, you can see that all these flows, they have this burstiness in them. And they are also like basic showing some chunking effects. Yeah, which is a lot better than the previous methods when they are trying to do the same type of encoding. Okay, so that's the evaluation of NetSSM. And one question I guess maybe you have is like, is NetSSM absolutely better than net diffusion? Uh, the answer is probably not. Um, the biggest reason is that all these autoregressive models, or whether it's some transformer-based models or this Mamba architecture, it's like the dependency itself is very sequential. However, in network traces, there are a lot of them um, which is not really sequential. For example, one field is like the packet size. The packet size, it appears very early in the header, but it's basically a computation of all the payload and everything, which appears much later in the generation process. So that is not like a like something very easy for autoregressive model to learn reversely. And we also did a recent paper on like quantifying the privacy implications of these generated data. Like NetSSM might be worse in terms of the privacy angle because it captures many multi-flow dynamics, which you can infer, for example, network topology, the type of devices behind it, because of we have like this more information on this. So it's another angle which I think makes this NetSSM slightly worse. So maybe like also on a retrospective angle, I think that maybe the best way to model this network traffic is more like video generation. Like within each packet, you can look at the dependencies more easily. But like they also have like a pretty good temporal components. The biggest difference is that like network traffic, they are very discrete and bursty, but like a videos, they are very evenly across the whole time domains. So basically here, yeah, that's just saying I think there are still like a lot of room for improvements. Cool. So now NetSSM is also open sourced. thanks to our student leaders, Chase and Andrew, you can see it online. And also, I want to give a big shout out to our initiative, netml.io. So this is an initiative led by my advisor, Professor Nick Finster from University of Chicago. So it's a central hub that contains a lot of information. So my advisor Nick, he started the first project of ML integrated into networking 20 years ago, and that was published on SIGCOMM. And since in our group, we have been working on every aspect of the ML cycle, life cycle, in networking. And it contains a lot of projects, a lot of publications, open source data sets, code, and also we open source a lot of courses on it. So if you are interested, feel free to check it out. Great. So I have talked about the data bottleneck. Now I will just briefly talk about like some use cases where we can use synthetic data to help to especially on reducing this data utilization cost. Because now previously we need to collect a lot of data, but now we can use this generative model to generate some targeted data. So this capacity alone gives us a lot of opportunity. I would be talking about very briefly on two use cases. One is from the security analytics angle. One is more network management. So the first case is about drift adaptation in network intrusion detection. The second is more about storage and the management of data there. So it will be very quick. Basically, I'll talk about the problem first. So the application we are looking at here is network intrusion detection. Basically, from the flows, we identify whether there's an attack or something like intrusion. Some hackers really try to hack into our internal networks. So there are a lot of like traces they can leave in our network traffic. But the big problem here is that network intrusion detection is very much an evolving problem. There are a lot of drift in it. For example, the benign traffic, they are evolving. And all the previous attacks where we have already observed, they are mutating because these attackers, they are trying to also evolve these attacks. And then on the top of that, there are new attacks happening. So that makes a lot of our models, which was previously trained, not really helpful when such changes happens. And on the top of that, it's very imbalanced. There are 99% of traffic which are like benign, and only 1% are malicious traffic. And if we really want to do the adaptation on it, a lot of time we need to find these anomalies first and at least try to not label them. And because the volume is too high and the labeling cost, it also takes a lot of expert to look across. That labeling cost is also very high. So here, let's try to use synthetic data to deal with this problem. This is an approach that what I call as generative active adaptation. So if we do not do anything, basically the model facing the drifted or unknown attacks, they will have a very low performance. However, we can actively sample some samples, and then we start to label it. There could be some labeling budget on using different methods. And one thing I think is really helpful is to augment this like a small portion of label data, for example, 1%. And we can use this generative augmentation to make it 10x. So by doing that, if we do retraining, we will have like a much higher performance. So basically, there's one result. I think it's very helpful to showcase that generative model can help to reduce the operational cost in such adaptation. So for example, here we have no adaptations on like baselines and the full NetGuard the system, we call it, using just 1% of labeling budget compared to like the full adaptation. You can see that like with just like 1% of labeling budget, we are able to achieve like much better performance. And you can basically like somewhat match our full adaptation approach. Yeah. So that's a case study one. The next case study I want to show is in this network data management, especially during storage. So this past network data is very important for many longitudinal analysis. And also if you want to have some network planning, basically that relies a lot on the previous data. That is a very high stake like decision. Basically, if you want to add more like servers, more capacities, it's usually $1 million question. And now within our real world internet service providers, they may generate like 10 terabytes of daily network traces. And that translates to cloud storage cost is nearly 900K US dollars. So that's actually not a small amount. And what's more challenging in the real world is that sometimes you simply are not allowed to store all the data. For example, many customers and internet service providers, they have the agreement on the retention policy, meaning that every, for example, 1 week, a month, or 2 years, they have to deprecate all the data they already collected. So that's a pity if we just let all the data go and without doing anything on them. So one solution to use this generative approach to help is actually let the model be the data proxy. So instead of storing all the raw data, we store the model weights trained on this data. So anytime we really want to use it, we just reconstruct the data from these model weights. We call this thing as deep generative compression. Yeah. So here is our system design. It's basically having two bases. One is this offline warm-up. We have basically like a base model. Then facing each data chunk, we fine-tune a model and only store, for example, the LoRa fine-tuned on this. Yeah. And then we put it into the model library. By doing this, we'll be able to reduce the storage cost by at least 82% compared to, for example, some really standard compression methods like gzip. Of course, you might be asking, okay, you're basically trading your compute with some savings in storage. That's true. And this is basically our preliminary result coming from a workshop paper. And now we have like a full paper which dealt with this problem. Even considering the compute, we can be more efficient than, for example, gzip. And the best of it, we can circumvent these compliance regulations. And basically, we can use the data as we really want it, and then you can reconstruct it. Okay, so here I want to also have a little bit shout out to my collaborators on these applications. We work with Professor VSC Carr at the CMU, and also like from UIUC, work with Professor Clara and her students. Good. So yeah, we're close to an end. So I want to share with you some bigger picture or visions I have in this direction of using synthetic data. I think it not only have helped us on both data side and system side to deal with these bottlenecks, we can also enable some, for example, future data and system foundations for the general direction of AI for ops. And we can work on a lot of applications beyond just networking. So the first direction, I think, is more innovations, leveraging the capacities of generative models. And for example, in our current world, we still basically train model on our siloed data set. We have many organizations, many campuses, many nations. They don't share the data across these data boundaries. So the default way to do this is like everybody just gets their own data and train their own model. However, with the help of synthetic data, we might be able to do more cross-silo collaborative training because we can all have some synthetic copies of the data and then put it together with our original data. We can also do some cross-conditioned augmentation. So basically, some traffic from, for example, US about web traffic, and we have the Hong Kong version of, for example, mobile traffic, and they can mix together and try to give us some newer traffic or some newer operational data. The third one is what I mentioned earlier briefly about is more about this longitudinal data replay. So before the data are obsolete, we turn them already into some like weights or knowledges, and then we can use it whenever we want. And based on these innovations, we can further pursue some orchestrations of the synthetic data. So basically, we can use a framework like this to improve many like machine learning models. So envision a framework like this. People send their siloed operation data to a third party, and this third party is able to make some complicated design choices. For example, what are the generative model to be used? Like what's the data partitioning strategy? And how much of data do people want to generate? And also how they are going to generate this data, like focusing on rare events, longitudinal, cross-condition, or cross-silo. So they can work across different combinations of these synthetic data and give them different weights with the goal of like maximizing some downstream models performance. So I want to explore a very clear deployable workflow inside an enterprise, which they can boost their ML model performance using synthetic data. One step further, we can automate the process of orchestration to optimization. So when the synthetic data is help us to build some stronger models, these models will constantly interact with our open world. So through these interactions, we'll be able to monitor the environment dynamics and quantify the rewards from the model's performance. So this is basically an RL process. And just like some, for example, circuit design automation, which is a very heavy RL process, this is also include many iterations of compilations. And basically, in here, what's more essential is to try to minimize the cycles or the trials for building a stronger model or generating the like best set of the data for downstream usages. Yeah. So finally, I think these principles are just beyond networking. It can be used on many other operational data sets which have like some siloed aspect of it. For example, Internet of Things, smart manufacturing, automobiles, or robotics, or like healthcare. So if you are interested in working on synthetic data for any type of your own domain knowledge, I think I will be really happy to collaborate and also work on like whether it's tabular or time series or some more domain specific modality. I think these general principles holds across different domains. So with this, yeah, thank you for your attention, and I'm happy to take some questions. Yeah, I know we are at the time, but yeah, thank you for your listening.
Any question?
Maybe we have one or two questions. It's time for.
There's a number quoted about the cost of saving
Uh-huh.
data.
Yeah.
That is really like, for example, I can buy cloud storage, right? I can buy 10 terabyte.
Yeah.
It's like much lower than that number. So what's the reason?
Oh, you mean here?
Yeah.
Oh,
I think if I buy 10 terabytes, but I don't know. I may spend like $200.
yeah, because it's accumulated like operation costs. Like basically this 10 terabyte could be like over 3,000 terabyte at the end of the year. So it's basically accumulating. So we're basically adding those for everyday operation. But yeah, in reality, maybe there are ways to reduce this cost. It largely depends on how you really store it. Yeah. Yeah. Any more questions, maybe from the online audience or oh, please.
Go back to the slide. So, uh, second approach with the second system.
Net SSM?
Yeah.
Okay.
And then
Yeah.
there's a slide that shows the accuracy.
Oh, here, you here?
Yeah. Not pretty sure about the definition of accuracy.
Oh, it's like a 10 class, or here in app level it's maybe 20 class. In service type it's 10 class classification. So to predict the right service or application here. Yeah. Yeah. So yeah, it's a classification problem.
So have they tried like training the data in one data set and then use it for another data set?
Yeah, that would be our drift problem. Yeah, so sure. Basically something like this. So these are basically all like there's no adapt is training on one data set and test on like maybe 1 month later. And yeah, I should have show it like on the same data set, but basically it's coming down from like 100 nearly 100% to like 68 F1 score here. Yeah. So yeah, sometimes it generalizes. Sometimes like with these continuous changes, it wouldn't generalize because, for example, attacks, there are always new attacks happening. Yeah.
So can I feel it as like generalization is not very important in your case?
Well, it's not necessarily, yeah. So yeah. So basically the goal of all our synthetic data is like we can then enable sharing different distributions and pull them together. So if we come from that perspective, we can train stronger models that generalizes in more different networking environments. So that's the generalization part. However, sometimes we do not have access to all this data. So for this use case, it's more about how you adapt them most efficiently, and synthetic data can also help that. Yeah. Okay. Sure.
There's some size on the other scenario, like here you just leverage the synthetic data, right?
Yeah.
Right now we know reinforcement learning is very useful with the limited scale of labels or annotations.
Yeah.
So what if compare it can actually it's maybe it can be indirect comparable to the reinforcement learning. So from the perspective of advantage of the two technical roadmaps.
You mean like
if given two models, one model is learned from synthetic data.
Yeah.
Another model is learned from the reinforcement learning with the limited scale of annotations.
Yeah.
So, who will win?
That's a great question. So the question is basically comparing one model doing synthetic data and another doing like RL with limited annotation. In my opinion, they are not contradictory. You can actually do RL on synthetic data, and yeah, but overall, yeah, it's hard to pick a winner. I think like currently we are working on these directions of direction 1, 2, 3 here. Well, I can see that compared to bare RL, uh, yeah, adding this layer of synthetic data definitely makes it better. And RL is a very good approach for us to seek the best recipe, the best candidate synthetic data sets. So yeah, honestly, it's hard to compare, but I think these are layered, very much layered. Yeah.
From my perspective,
Uh-huh.
to as of my knowledge, in the recent years, the tech companies like OpenAI, they just OpenAI, Google, and Meta and Microsoft Research, they apply reinforcement learning to
Yeah.
to enhance the models.
Right.
Instead of generate a bunch of synthetic data to train or fine tune their language models.
I think they're doing both. Yeah. For example, even from like DeepSeek R1, they do a lot of synthetic data generation. And in there, they actually use some reward guided methods to pick the best synthetic data from this.
Then I will have a follow-up question is
Uh-huh.
how they design a real measurement to prevent accumulative errors from synthetic data.
That's really a good question because if I remember correctly, there are some Nature articles really trying to deal with this problem of the curse of recursion. Basically, they're saying like, okay, I have seed data, and then we generate some synthetic data on that, and then we recursively generate another set of synthetic data on this combination, and so forth. So the improvement is only seen at like maybe the second iteration. And then later you will just like a drop, right? This is how they argue that. But later in the community, people are trying to deal with this issue. They found that if we continuously add some real data, for example, like images, like we continuously add like a new month of data inside it, and it will continue to grow on the capacity of it. Yeah, basically it's like a recursive approach versus like a accumulated approach. And I think that's also the beauty of maybe more underlying orchestration or optimization. You have to select this data in an intelligent way instead of just recursively synthesize them. Yeah. So I can share you more on this, like some papers, some more discussions offline. Yeah.
I think your study problem is also comparable to
Like the healthcare.
no, just not healthcare. It's like a stock market trading. Like they have count trading data,
Yeah.
and
Yeah.
you have trading from all the like stock market customer.
Yeah.
and
Yeah.
Have traffic everywhere.
Uh-huh.
Yeah, I think if you're interested, you can expand your research to that area. as
Yes,
well.
yes, exactly.
You can also detect the unusual transaction just as
Yeah.
detect the
Yes.
intruder, right?
Right. Yeah.
They is a healthy care because there have the common issue about the data privacy. We cannot share the data between institute or hospital, so we have
Yeah.
the same issue. Okay, the synthetic data maybe is a kind of the way.
Yeah, I think I saw some papers on using synthetic data to do healthcare issues. Yeah.
So
Oh,
here.
yeah.
Thing.
Right. Well, there are some professor from Alberta who is trying to use RL here, and then they're also working on similar issues. Basically, they have a lot of patient records, which is impossible to share.
The healthcare regulation.
Yeah.
Check recent paper. I think Neuralib's best paper in 2005. They also about difference memorization.
Uh-huh.
If the healthcare
healthcare regulator found actually different model can memorize a large amount of information, then they said, yeah, you can't even
Yeah.
share the model.
Right.
Now, I think they probably haven't really looked at this part yet. Many people use generative model as a way to share data, but
Yeah.
recent studies, they also pay a lot of attention how much the different model memorize data and how much they generalize, just as you
Right.
have shown.
Yeah. That's actually a really good point. And I think the notion of privacy or security of these, or basically the safety of the models themselves in this setting is very interesting. And in my domain, I think it's like, it's not even about conventional wisdom of, for example, DP or whatever. They're basically trying to protect the identity of each record. Um, Here, I think it's more about some predefined secrets, which is a attribute of the whole data set. It's mostly like a function of the data set you are going to share. I will use networks as an example. So if people are sharing network data, they don't want to leak many business secret information, such as like the network topology, their traffic volume, which indicates their users, the amount of users, and then that also have a lot of influence on their stock prices and stuff. So I think this can um, this basically motivates a line of work which is trying to not just like protect each records and their identity, but also protecting a function of the data set or even like a SQL query of the data set. Yeah, adding noises on these distributions instead of like each column. Yeah, I think it's much more different than that. So I think that we can have a lot of more work in this domain. Yeah. Recently we are also working with uh, like Professor Julia from CMU. We discussed some approaches which can really add noises into these functional distributions. Yeah. Okay. Yeah. Thanks everybody. Thank you for staying longer than expected. And yeah, thank you so much. And yeah, thank you for joining us online. Thank you everybody. Yeah.